Good morning and welcome back to the lecture session. Today's lecture is basically continuation of the last lecture where we had discussed about the concept of cyber physical production systems and the smart manufacturing in the context of Industry 4.0. And the concept of the understanding or implementation of smart manufacturing and the cyber physical production system would not be possible unless the DT, that is the digital twin, is understood in its true spirit. That is the key enabling technology behind the realization of the smart manufacturing and the CPPS. So that is why the today's lecture is having the title digital twin and the key enabling technology of the CPPS. If you correlate with the last lecture, I myself intentionally have maintained the three of the previous slides just to maintain the consistency and for the better understanding. So once again, just for the purpose of recapitulation, to have a look about the cyber physical production system, how it looks like. So categorically or very fundamentally, it is the integration of the physical shop floor of the physical systems with the cyber world for communication, computation and control through the enhanced decision making. So in the lower half, there is a symbolic representation of the physical shop floor where one physical item in the form of an articulated robot is considered. There are a lot of sensors, sensory system, readers which are responsible for acquiring the data from the object or from the equipment, and those data would be transferred to the cyber world through the appropriate networking system to convert this data to the information, so that with the help of different AI tools or the data analytic approaches and the requisite software tools can be accessed to the cloud. Of course, there are a lot of data management aspects which ought to be performed before taking up this analysis part. So eventually, the main motto is that in the cyber world, we have to carry out a lot of analysis of the data so that useful information which will be coming out as a consequence of the analysis would be utilized for the decision making. For the decision making, it may be utilized for the optimization, for the simulation, for prediction, for awareness, all higher level decision making. Generically, I had mentioned in the last class, generically called as a self-X capability. So for the control purpose, information will again feedback from the cyber world to the physical world to complete the loop. So a CPPS is basically integration of the physical manufacturing equipment and sensors with the virtual world through the internet, obviously coupled with big data analytics, AI and cloud computing, so as to convert the existing manufacturing system to be more powerful and smart through enhanced decision making, computing and computation. Another slide that is also basically was available in the last lecture, that is the 5C architecture. I am not going to the details, just for the maintaining the consistency and for memorization purpose and to correlate the previous lecture with today's one. So this 5C architecture I have written. So it starts with the smart connection level in the sensory system in the shop floor, then data to information conversion level. In the cyber level, we will have the twin model. So today we will emphasize or focus our attention to this twin model. What eventually we will be able to do, that it will eventually lead to the higher level of decision making. And finally, what the system is aspiring for, that is self-X capability, self-configuration, self-organization, self-maintenance, self-awareness, self-optimization, any higher level decision making, but without the intervention of the human beings. And entire activity is taken care of or is based on the data intensive technology. Digital twin. So digital twin is basically the virtual entity in the manufacturing which is instrumental and acts as a key enabler of the same, that is the smart manufacturing and CPPS. The integration of the physical world and the virtual world is carried out by communication, computation and control. So the connection between the physical world and the cyber world and the entire data flow and information flow and along with the high level or enhanced decision making, this can be very comprehensively captured or represented by 3C. One is communication, then computation, and finally control. So through the communication, we establish the data flow, or we create a path or platform so that data can be sent continuously in real time from the shop floor to the cyber world. So communication is the first step. Once data reaches in the cyber world, then with the help of different AI techniques and the data analytic tool techniques, using different software tools, higher level decision making is carried out. So that invariably involves the structure of computation. So once computation is carried out, it will lead to final actionable conclusion in the form of decision making. So eventually, what we are supposed to do for better output, to improve the efficiency of the plant and machinery, the control commands should flow again back from the cyber world to the physical world to better control the process, and thereby we can improve the efficiency, productivity, and other key performance indicators of the plant and the machinery of the process. So 3C is the very comprehensive and simplified approach to understand the entire spectrum of this connectivity or the integration between the physical world and the cyber world: communication, computation, and control. So before let me explain a little bit about the digital twin. So it is the virtual entity in the manufacturing which is instrumental. How will we create this digital twin? So in the digital world we have a replica. That is what exactly is called twin. So this twin is not in the physical form, but it is the digital representation of the physical world, of the physical process, of the physical equipment, or the product, whatever it may be. That is what exactly is called the digital twin. So in the digital twin, data will flow, data will flow from the shop floor, and after the organization and the computation, resulting information will be utilized for the controlling purpose. Now, before going to the detail about the digital twin, let us, it is imperative to discuss some earlier primitive or simpler version of the digital twin in the form of digital model and digital shadow. Digital model is basically a digital version of an existing physical system, but the limitation is that there is no automatic data exchange between the physical model and the digital model. Now, naturally, very pertinent questions that may arise in our mind. If there is no possibility in the scope of the data transmission, then how to implement the concept of digital twin? But when it was conceived first, the objective was something like this. At that time, maybe in the, I will come to the later slide, as early as 2003, Professor Michael Gibbs had conceived the idea of digital twin. At that time, internet and the connectivity was not so powerful as it is today. Even the lot of software and the computation tools was not available. But the idea was something like that, that the physical data from the physical equipment or the processes would be captured by some means, and it would be transferred somewhere else for carrying out the calculation, computation, which will be eventually used for better decision making, and which will lead to better control the process. So the very primitive approach or primitive version of the digital twin was digital model, but the major limitation was there was no automatic data exchange between the physical model and the digital model. A little bit advanced modification of the digital model is the digital shadow. In the digital shadow, data flows only from the physical object to the digital model. So there are possibility of data and information propagation in two ways, from physical to cyber and then cyber to physical back. From the physical to cyber, they are in the form of raw data, and from the cyber to physical, it is in the form of information that will lead to actionable conclusions. So in the digital shadow, the data flows only from the physical object to the digital model, or sorry, digital physical object actually it should be the digital world. Sorry, it needs to be corrected. Digital world. That means automatic data flow is possible, but the reverse, to close the loop, that was not permissible. So at least for the purpose of decision making, for the purpose of computation, it is possible to capture the data through the sensory system and the data acquisition system, and over the internet it is possible to send or communicate the data to the digital world. So digital shadow is the improvement of over the digital model, and digital twin, it allows fully integration by establishing two-way communication. So data and information transfer are completely bidirectional and they are fully integrated in both directions. So in the current days, due to the advancement of internet and communication technologies, and of course the availability of the powerful computational software, it is now possible to realize the digital twin in its true spirit. But nevertheless, it has started with a rather simple and the primitive version as a digital model. Then one step ahead, digital shadow, and finally, it is the data transfer is when fully explored, we can realize the digital twin. So this is the pictorial representation of this the comparison between the digital model, digital shadow, and the digital twin. So this dotted line shows that this is manual data flow. So automatic objective is there to accomplish automatic data flow, but that was not possible. So if you want to convey certain information on the data, we have to rely on the manual mode. So this dotted line and this particular arrow symbolizes that to establish connectivity between the physical and the digital object, we have to rely on the manual mode. Automatic data and information propagation transfer was not possible. In the advanced version, digital shadow, this continuous arrow line that symbolizes that data flow from the physical to the digital is possible, but automatic information propagation back to physical from the digital was not possible. But when we can realize the complete digital twin, both were full integration to the data and information transfer is possible. So this particular graphical representation gives us a glimpse how to distinguish between the three different versions of the digital twin. As I was talking about, the early concept of DT dates back to 2003 and credited to Michael Reeves, who conceived the idea of virtual representation of physical product in a very humble and modest way by collecting data manually using paper-based system. As I was talking about, there was no possibility of automatic data transfer, so he had to rely on the paper-based system. The way we write some data during experimentation in our conventional flow. So we capture the data, we observe the data, then note it on a paper and take it to somewhere else for the purpose of calculation. So by collecting data manually using paper-based system in the context of product life cycle management. So according to Gibbs, three distinct activities popularly known as the use case, namely the conceptualization, comparison, and collaboration of the backbone of the next generation problem solving and innovation. So Professor Gibbs had conceived in the 2003 that eventually if we want to go for better control of the process, if we want to augment the efficiency, productivity and other performance indicator of the plant and the machinery, we have to develop or we have to rely on automatic transfer of that data and information. So this is a photograph of the image which was developed by Professor Gibbs. Apparently, if you take a look, that it will give an idea that both are identical basically. Actually, exactly, this is identical. This is the physical object and this is its corresponding digital twin of the digital image of the digital part. How to distinguish and how to differentiate? You see, if you have a closer look, you will see in the background there is a combination of 0, 1, 0, 1, 0, 1. That means it is the data is digitized. So this particular is a digitized image available in the cyber world of what? Of the physical product which is lying somewhere in the shop floor. And how to establish connectivity? So from the physical data will be the data pertaining to the physical object or the process would be transferred to the digital world to create this digital twin, and effective results in the form of information will be sent back from the digital world to the physical world by using information. So this is the picture which completely depicts the theme and deeper insight of this digital twin. How data transfer takes place between the physical object and the cyber world, and how to create the corresponding virtual twin or the digital twin. Afterwards, the first major breakthrough in DT application was reported by NASA and the US Air Force in 2012 for the health maintenance and predicting the residual life of aerospace vehicle. So afterwards, the major breakthrough was achieved by the NASA in the health maintenance and predicting the residual life of aerospace vehicle. Afterwards, will come what are the capabilities of the digital twin. So predicting the residual life or predicting the failure possibility of different key components, that is also one of the key parameter, or I would say key capability of the digital twin. With the evolution of IC, that is information communication technology, in the recent years, the concept of DT has matured enough and its scope has flourished by leaps and bounds so as to embrace it as a key performer in realizing SM and CPPS in the context of Industry 4.0. Now, in the 21st century or the early 21st century, there has been tremendous development in information communication technology, which makes it possible to realize digital twin in its true perspective. So, a digital twin is a data-driven paradigm. As I told in the last lecture also, that this SM and CPPS is basically a data-driven or data-intensive paradigm. So, digital twin is a data-driven paradigm, and in essence, it is a mirror image or digital abstraction of physical shop floor and the products. The real-time, what you had discussed earlier, that is same thing. Once again, I have incorporated in a separate slide the key capabilities or the key attributes. The real-time data is collected by various sensors and the IoT devices from the product and equipment in the shop floor, and then transferred it to the digital world through communication network or analysis. Once it is carried out, the analysis part is done, then useful information generated by processing raw data using varieties of techniques such as AI/ML, big data analytics, and cloud computing, etc., in the digital space is utilized to control the processes in the physical world for the purpose of optimization, prediction, and other similar value-added functions. So that is the key requirement or the key objectives of the digital twin. Now twin. So all of a sudden it is not possible to create the twin. So physical object is there. So continuously in the real time, the data will be communicated from the physical world to the cyber world, and the process of create the digital model or the replica, that is what exactly is called twinning. So the twinning is therefore a cyclic process connecting the physical world and the cyber world through data transfer, and cyber to physical world through useful information propagation, such that virtual copy becomes the mirror image of the physical world and vice versa. As there is a process in the physical world, so the status of the state, afterwards we discuss the properties of the key attributes. The status of the state keeps on changing. So whatever changes are taking place in real time in the physical world, that must be reflected in the corresponding virtual world, in the corresponding virtual copy of the virtual model. Okay, so that process is called basically the twin. And both physical equipment and its virtual part co-evolve dynamically through their entire life cycle. It is not for one time. So long the process will continue, so long the product keeps on evolving, the digital twin will also keep on evolving accordingly. This is the parameter which we are talking about. There are certain key parameters. These parameters refers to the types of data, information, and processes that are communicated between the physical and the virtual twin. Because the entire activity is taken care of by the data and information. But it is what data, what information that should be relevant to that particular process of the product or thus system. Okay, so those data at any particular instance is whatever may be the process or the product in the field of our metal cutting. We can consider the maybe the cutting parameters like speed, feed, depth of cut, and at the same time some other measured parameters like cutting force, vibration, temperature rise. So these are the different parameters that describes the state of affairs of that particular process. State, it represents the current condition at any particular instant. What are the value of speed, feed, depth of cut, the cutting force encountered or generated, the vibration level, the temperature rise. So at any particular point of time, the values of different parameters describe its state. So it is analogous to the thermodynamic process. When a particular system undergoes a process from state point 1 to state point 2, it undergoes a path. So incrementally, which we generically call quasi-static process. So individual state point, which is basically the locus of those points, are nothing but the state. So this state in case of digital twin is equivalent or the tantamount to thermodynamic process. Fidelity, this is a very interesting and most important attributes of a digital twin. It describes the number of parameters, its accuracy and the level of abstraction. So the comprehensively, we want to create the complete digital twin which will be 100% identical to that of its physical counterpart. While doing so, while transferring the data, it may not be possible that the sensory data which are captured and sent may not completely capture the true data or the actual data. There will be some inaccuracy, some error. So the success depends on how many parameters we consider to fully describe the process of the product, their accurate values, and to what extent at the level of abstraction, that is also important. So these three attributes together define the fidelity. We call high fidelity data set is essential to perfectly generate create the digital twin. So twinning, as I told, it implies how accurately and closely the virtual model can be captured or represent its physical counterpart. And twinning rate, because there is a continuous data flow, so the frequency of the data flow, the way the virtual model is being generated, how fast that describes the twinning rate. So it represents the rate of speed at which twinning takes place. Ability represents the current condition of both the physical and the virtual twins, or the current values for each of the measured parameters. Whatever changes are taking place in the physical world, that should be reflected immediately, almost with any loss of time or delay in time in the corresponding virtual world. So that is the necessity of the twinning, and the rate at which this twinning of the digital image generation takes place, that is called twinning rate. Now another way to consider digital twin for what is the level, that is the hierarchy for a complete product or a very complex product or for a particular process. So depending on the level or the complexity, it can have three different hierarchy level known as unit level, system level and system of system level. The most fundamental and atomic is the unit level. The most fundamental basic atomic level of application is known as the unit level. Such a one single machine tool. Afterwards, I will show you one machine tool digital twin. So one complete machine tool which is standalone, or a robot or a Korean measuring machine, that can be considered as a unit level. But in a factory, there may be possibility that several CNC machines are engaged to execute certain amount of or some specific goal or the tasks. So in that case, we can say that it is a system level. So when a number of unit level entities cooperate and collaborate, the integration of data and services across all these entities are required so as to move up to the next level of hierarchy known as system level DT. In this context, it is imperative to say that in IT fraternity there is this approach called agent-based system, Thoronic system, agent-based system, where all the machines are considered as the intelligent, and they are engaged in a team and they collaborate to carry out a particular task. It is inspired from the societal system. Whenever a particular task is not possible to execute it by a single individual, then we take the help of others, or sometimes we offer help to others. So these a group of people, similarly, a group of machines collaboratively are engaged or utilized to solve a complex problem, each one having a definite amount or the portion of the task, and collectively when they are all put together, we can have the global output of the system. So that is what exactly is called the system level. So agent-based approach is extremely important to realize DT in the system level. And when we go for more such complex systems, such as an air cap or a different branch that needs to be connected, then when several system level are logically connected to a network, then the capability can be augmented, leading to the development of system level, and which is considered as the highest level of digital twin. This is one just example I have taken from a paper contributed by Liu and Zhu in 2018. A CNC machine tool. So this is a schematic representation of a CNC machine tool. So in the second block of our DAQ, data acquisition devices. So a lot of sensors are deployed in the shop floor, which will be responsible for capturing real life data from the machine, and those real life data through the internet, through your network, it should be sent or should be transferred to the machine tool digital twin. And your process parameters, what I was talking about, speed, feed, depth of cut, those can be automatically displayed in the machine tool, and so those also can be transferred to the cyber world for necessary calculation and its utilization. And in the initial slide, you had perhaps noticed that I had mentioned about a term called data management. So before taking up the data or to make this data set amenable for further processing, lot of PPPG, calculation, your filtering, processing, pre-processing, segmentation, data mining, these are required. Interoperability aspect also ought to be considered and accomplished. So this is what exactly is called the information model, and a database will be created. And this machine tool, cyber twin, is responsible for establishing machine-to-machine interfaces. What are the key capabilities? In this pink color block, you see lot of algorithms and analytics will be performed. PHM algorithm. PHM stands for predictive health monitoring. Optimization algorithm, high fidelity simulation, AR assisted visualization, and finally decision making. So all sorts of high level decision making can be carried out by using different algorithm, analytics, and software tools which can be accessed from the cloud. Now the result of information can be sent back to eventually it has to be transferred to the machine tool back again. So there is a possibility of the provision of the two-way data transfer. And the right side, the smart HMI symbolizes smart human machine interface. It may be a tablet, it may be your laptop, it may be what is called your Android phone. So with any devices, we can regulate or adjust the process parameters. So this is how it is. So from the machine to receive, this blue color arrow symbolizes that final result obtained after the decision making that can be fed back to the CNC machine tool once again. That is in the software level for eventual control, better control of the process. So it is a basically similarly representation for the a sample machine tool digital twin. But machine tool digital twin is not the sole area of the application. The same concept logically can be extended for any equipment or any product as well. So some prominent application area that can be considered or can be carried out as the part of DT capability, the analytical assessment, predictive diagnosis, simulation, PHM, prognostic health monitoring, simulation, scheduling, performance optimization, which I had told earlier as well. So I am not repeating. Accordingly, we see that these are not yet been implemented in the factory level. Then what is the utility? No. Already some leading industry houses all across the globe, they have implemented in their different activities to accrue the potential benefit of the DT capability. So some such application I have considered. Siemens applied DTs for the power system and wastewater plant. General Electric developed the hardware and software for establishing the wind farm DT. Furthermore, GE applied the DT in other fields such as locomotive and healthcare. British Petroleum applied the DT to address the challenges of monitoring and maintaining the oil gas facilities located in remote areas. Some other Airbus aims to realize the digitalization of the factory through DT-based solution. It developed an assembly line DT to monitor the production process and optimize the operational efficiency. Tesla, the leading EV manufacturer. So Tesla collects a range of data from its vehicles and analyzes them to its servers for different purposes such as detection and resolving issues in its vehicles and developing new products and services. So in the coming days, it is expected that it will flourish and its appeal is so universal that in other industries also will be benefited immensely to the DP capabilities. So to this end, some concluding remarks. Since there is no global consensus on DT modeling, one can develop it to suit its own requirements. So it is the prerogative of the individual organization or the department to design and develop its own DT, that is a digital twin, to satisfy his or her intended objective. Seamless data transfer from heterogeneous sources is a big challenge. I was talking about the term interoperability. Varieties of data from different sources, from different sensors, all are not from the same vendor or the same manufacturer. So there will be possibility of data disparity. So interoperability is the property so that there would not be any difficulty in transferring the data from one location to other location, so that data integration is permissible. So that property that enables or that allows all sorts of data to be transferred without any difficulties, that is called interoperability. So that, but although it is in theory it looks very simple, but there is a real life difficulty. So that aspect needs to be considered. Without open source controller, feedback control is difficult to automate. Particularly, this third part is extremely relevant in case of CNC machine tools, because the machine tool controller are usually proprietary in nature. So that implies that it will not allow any external commands to take care or to implement. So that is a challenge. In that case, the controller should be open controller type of nature, so that it will allow the external commands to execute. Network connectivity is another crucial issue. Needs to be addressed to ensure two-way data transfer. So, as you know from your difficulty that we encountered in our mobile phones, quite often there is a disturbance or disruption in the net connection. So that connectivity obviously ought to be ensured, because that is the backbone of your data and information propagation. Gateway like MT Connect is highly expensive and not readily available in the market till now. This MT Connect, this is a typical device which is exclusively meant for the machine tool purpose for collecting the data and to send over internet to the digital world. It is very costly and it is all over the globe. It is not highly accessible. So some alternative gateways are designed and developed by some other competitors, but expected that due to the rise in the popularity, some vendors will definitely coming up with some better solution which are affordable. Nevertheless, the rise in DT research will explore the opportunities to elevate it to a greater height, so as to embrace it for its use in varieties of applications. So the way the development, technological advancement are taking place very fast in the digital area, so there is a real possibility that digital will flourish to a much more extent, and academia as well as the industry will be immensely benefited from this DT capability. So that's all. Afterwards, I will also prepare one another lecture over the real machine tool capability with some mathematical functions and our own developed digital tool. So thank you very much. I believe that you have got certain input about the Industry 4.0, what is vision, what is cyber physical production system and smart manufacturing, and today the most important of the backbone part, that is the enabling technology, digital twin. So these two lectures comprehensively give some idea about the current days of the status of the state of the art and the cutting edge technology application in compliance with the vision of Industry 4.0 to augment the performance of the plant and machinery. Thank you very much.